now we have more tests to tell whether something that possibly will converge will definitely converge. The first test, which could be used for any series to see if it converges or not, is called the integral test. Okay? Integral test says if a function is positive, continuous, and decreasing, and the terms can be listed by a function, some terms from a series can be listed by the function, then look at the unbounded area starting from whatever value that we're starting from to infinity, and look at the sum of the series, either both converge or both diverge. Okay? So we're looking at f of x is equal to 1 over x squared. Well, that would kind of go along with a to the n is 1 over n squared. If I can find the integral from 1 to infinity of 1 over x squared dx, and this converges, then I know that the sum, n starting from 1 and going to infinity, of 1 over n squared will also converge. Okay? So I can find this because I know how to do these improper integrals. Okay? That was from the last lesson of the last unit. This is x to the negative second. This becomes negative 1 over x, the change between 1 and infinity. I'm skipping the whole limit problem, but you understand. And this does converge. You get negative 1 over infinity plus 1. So this converges. Since you know that converges, that converges. Okay? How can we be sure that it converges? Well, if you think about it, I know that this entire area, this unbounded area that goes on for forever and forever and forever, that's going to approach a number. It approaches 1. Okay, negative 1 over infinity ends up being 0 plus 1. It approaches 1. Well, let's think about what this can look like on a graph like that. Okay, where a sub n is 1 over n squared. Well, I'm going to be adding up these values. Be adding up the value here with this value here and this value here and there. So I'm adding up all those dots as whole numbers. What does that look like in terms of area? If I add up this number plus this number plus this number plus this number plus this number. Right? It's a weird question. But if you think about it, we're doing an infinite sum of width times height here. Well, you could think of this number having a width of 1. So if this is, 1, this is 1. If this is 2, this ends up being 1/4. Well, you could think of adding 1/4 by just taking this area here, width of 1. Right? And then I add this, and I add this, and I add that. Well, if this area converges, and all of a sudden I'm looking at these areas that are just these kind of like a Riemann sum, we know this is going to be a little bit underneath it, and it's also going to converge. This is the visual representation of the sum, really starting from 2, because I'm starting on this one, on the second one, to infinity of a sub n of 1 over n squared. And that's going to be less than this area, and that's definitely going to converge. If you think about, if this red area converges and we're talking about less, that's going to converge. Well, if I wanted to change it to 1 over to n starting from 1, I would just add 1 extra rectangle. I would need to add this one here. And if we have a converging value plus 1, it's also going to be a converging value. Okay? So that's the integral test. Kind of equates, improper integrals to some summations, which are great. Okay? Now let's look at if we can compare the specific values between this improper integral and this here. So an example of a question is, if the function is positive decreasing such that the area from 1 to infinity is 5, and this a sub n is equal to f sub n, is the sum from 1 to infinity of a sub n more or less equal to 5, or do you not know? Okay, so let's think about this. We have a graph of a positive decreasing function. We're told that this area from 1 to infinity is 5. What would be the visual representation of this sum? Well, you can think about it instead of what I did in the previous example, which kind of shows that it will converge. In this example, you could say, okay, I need to add this term, that term, that term, that term, and that term, all the way to infinity. Visually, how do we add that term? It would be this y value times 1. So there's my length there. Then the next term times 1. That'll be adding the first term with my second term, plus my third term, plus my fourth term. And all of a sudden, this area in green would be that guy, whereas the area in red was this guy. Since this converges, we know this converges. By the integral test. And we know by the visual representation that its sum is going to be more than 5. How much more than? I don't know. But I know it's going to be more than. Okay? Do we understand this whole idea of doing this Riemann sum? It's because I'm trying to add this value. Well, how do I add this value in terms of area? It would be this y value times 1. Boom. Plus this y value times 1. Plus this y value times 1. And it looks like a left Riemann sum. Okay? So that's the integral test. What else can we do with the integral test? We can look at certain series, whether they converge or diverge. And the integral test would be the only test that really does a good job of figuring out if this is going to converge or diverge. Okay? The key is this sum will converge if this converges, or it will diverge if this diverges. Which means I have to find the integral, the antiderivative of 1 over x log x. If we recall from back in the day, we have to use u substitution to find this antiderivative. U is equal to log x, du is equal to 1 over x dx, dx is equal to x du. This ends up being 1 over x u times x du. The x's cancel. The antiderivative is log u, or log absolute log x. We'd find the change in that between 1 and infinity, which is log of infinity. We're not supposed to do this, of course, plugging in infinity for x. We're supposed to use that limit, but I don't have time. So minus log of 1. This is just 0. We should have started from 2, actually. Log of 2. So we can find this value, but this would be approaching infinity. So this is approaching infinity. That means we're going to diverge, which means this series definitely diverges. Even though when we looked at the nth term, the limit as n approaches infinity, that equals 0, and we say, oh, that series possibly converges, the integral test just shows me that this definitely diverges. Okay? Here's an example of something where the limit will approach 0. However, when you add the terms up, they won't converge toward the value. It'll just continue to increase and increase and increase. Okay? Let's look at another one. 1 over n. Okay? Well, we've looked at this before. We found that this improper integral of 1 over x from 1 to infinity, 1 to infinity of 1 over x, antiderivative log x from 1 to infinity, this ends up diverging. This is log of infinity minus log of 1, infinity. That diverges. That means the series, the sum n starting from 1 and going to infinity of 1 over n, which will approach 0, diverges by the integral test. If one does one thing, the other one's going to do the same thing. Okay? Now, again, this series, we say, possibly converges. Its limit as n approaches infinity is 0. But as we start adding up the terms, they are not going to get closer and closer to a value. They'll continue to increase. It will diverge even though the limit is equal to 0. This is a famous series. This is called the Harmonic Series. Okay? This sum, starting from 1, going to infinity of 1 over n, which is 1 plus 1/2 plus 1/3 plus 1/4, et cetera, et cetera, et cetera. This is a divergent series. Proven by the integral test, but now you will just know that this harmonic series is divergent. Even though you think, oh, I'm just adding a fourth, then a fifth, then a sixth, then a seventh. Aren't I adding smaller and smaller values? Won't we approach something? Actually, no, we won't. It'll just continue to increase, increase, increase. Slowly, but it will continue to increase. Okay? Sweet. Now, let's look at a p-series. A p-series is any kind of sum where we have 1 over n to the p. The integral test can help us for all of these series, like 1 over n cubed, 1 over root n, 1 over n root n, because I can use the integral test for all of them. Okay? And what we'll find out is we can come up with a rule for any of these series that looks like this. Now, all of these will approach 0, so they're all possibly convergent. But we will use the integral test, do the improper integral, and see, are they actually convergent or are they divergent? So I have to take the antiderivative of 1 over x to the third. This is x to the negative third. This will be x to the negative second times negative a half. So that's negative 1 over 2x squared. From 1 to infinity, we plug this in, we'd get negative 1 over infinity minus negative 1 over 2. That'll end up converging. So 1 over n cubed will converge. Let's look at 1 over root n. Its sum. Well, let's do the improper integral from 1 to infinity of 1 over root x. The antiderivative of x to the negative half is x to the 1/2 times 2. So this is 2 root x. From 1 to infinity, this will end up diverging, right? Because we have 2 root infinity, which is infinity minus 2. It's definitely going to be infinity. That means 1 over root n, though its limit is infinity, limit as n approaches infinity is 0, this will diverge. Okay, and we can kind of do the same thing here to show that this one converges. And what we can see, and we can kind of extrapolate all this work, is a rule for a p-series. Okay, if we are looking at the sum starting from 1 going to infinity of 1 over n to a p, where p is a number, this will converge if the number is greater than 1. It will diverge if the number is less than 1. or equal to 1, of course. When P equals 1, we have the harmonic series. Okay, so now we talked about geometric series, how they look when they converge. Now we're talking about P series, how they look when they converge. We can look at these series. Do they converge or diverge? Let's change this to 1. This is 1 over the 5th root of n. That can be written as 1 over n to the 1/5. The 1/5 is less than 1. I know this is going to diverge. Less than or equal to 1, really. I have 1 over n to the 5/3. The 5/3 is greater than 1. I know this will definitely converge. Now, unlike the geometric series, there is no set formula to find what it converges to. All we know is that it's going to converge. Okay, the geometric series especially, we're able to extrapolate things and find the formula for its sum, but I don't know the sum for a P series. But I do know if it converges or diverges. Okay, let's look at a couple others. 1 over n to the pi. Pi is greater than 1. So we're going to converge. This is written out. We got to figure out what it is. Then once we figure out what it is, how it's created, we can figure out if it's going to converge or diverge. This is 1 plus. I'm going to rewrite this not as cubed root of 4, cubed root of 9, but as the cubed root of 2 squared. This would be the cubed root of 3 squared. This would be the cubed root of 4 squared. And I could say, okay, that's the sum, n starting from 1 going to infinity, of 1 over n to the 2/3 power. 2/3 is less than or equal to 1. We're going to diverge. Now, that's for a specific P series. We are going to get into some tests that can be kind of generalized for lots of different series. Okay? Doesn't have to look a specific way like a P series or a geometric series. Okay? We have enough series that we know are convergent or divergent to now establish some comparisons between the series. And through these comparisons, we will be able to figure out if the series will converge or diverge. For example, let's look at the series 1 over n squared. Does this converge or diverge? Converge. The 2 is greater than or equal to 1. Excellent. Well, let's take another series, Bn, and let's just call it less than An. How much less than doesn't matter. So I'm going to put it like half the distance. So it's half the value that we're adding up. Well, if I know that An, which is 1 over n squared, converges, what do you think Bn does? Probably converges, right? If I'm adding up these values and it approaches one value, and then I add up smaller values, those smaller values are going to add up to most likely be a finite value as well. But let's also bring in some other ones, Cn, which is bigger than An. How much bigger? I don't know. In this situation, I know that A and N converges, but if I'm talking about values that are larger, I'm not sure how much larger. I'm not sure whether or not this Cn is going to converge or diverge. I just don't know. Okay, so if I start with a converging series, and I know that another series is less than that converging series, that less than series is going to be convergent as well. A quick example of these is like if I look at 1 over 3n squared, or 1 over n squared plus 1. If I increase my denominator, I know that my fractions are going to be smaller. Okay, increasing the bottom makes the fraction smaller. Well, by comparison, I know that this is going to be less than 1 over n squared, and this is also less than 1 over n squared. I know definitively that this will also converge. By a direct comparison. Okay? Well, what if we start out with a series that diverges, like 1 over n? 1 over n diverges. Looks just like 1 over n squared, right? Just maybe the dots are a little bit higher. Well, let's again start with a bn, which is less than an. Well, I don't know how much less than it is. And since I don't know how much less it is, if I start with a diverging series, and I look at this guy, I'm not sure if it's going to be less than enough to also be a diverging series. I'm not going to know. Could converge, could diverge, not sure. But if we look at this C of n, which is greater than A of n, if I start with a sum that is divergent, and I'm taking values that are greater, I can go ahead and assume confidently that that C of n, that greater series, is also going to be divergent. A of n is divergent. C of n is greater than A of n. C of n must be divergent as well. If we start with something that is convergent, well, smaller values will also be convergent. So we can look at some terms, some series generated by like 3 over n, or yeah, something like that. We increase the numerator, and since I increase the numerator, I know this is going to be larger than 1 over n. Since it's larger than 1 over n, I know that it's going to diverge. Okay? This is a perfect series that the direct comparison test shows will converge or diverge. The absolute value of sine n over n squared. Now I think about if I plug in bigger and bigger values for n, what sine absolute of sine n, what it'll do. I know sine goes up to 1 and down to negative 1. So the absolute value has got to be stuck between 0 and 1. Okay? So it's like a fraction that's going to be in my numerator. Well, if I compare this to 1 over n squared, which I know converges because it's a p series with the p greater than 2, we can tell, since this is going to be like a fraction in the numerator, my numerator is going to be smaller, that this ends up being a smaller series than 1 over n squared. Since 1 over n squared converges and absolute of sine n over n squared is less than 1 over n squared, I also know that this converges. Okay, let's talk about the limit comparison test now. This is a test that is actually easier to use than direct comparison, but it follows along with the direct comparison test. Okay, the limit comparison test says that if both A of n is positive and B of n is positive, it's important that they're positive. If we look at the limits as n approaches infinity of the quotient of the two, now it doesn't matter which one's on top, A of n or B of n, if this equals some value L, L must be a finite value, it can't be infinity, and it must be positive. So it can't be 0. Then, and this is similar to kind of the integral test, A of n and B of n either both converge or both diverge. Okay, it's a simple test. We've been doing infinite limits a lot. So being able to just put some quotient together, evaluate the limit as n approaches infinity, get a value or don't get a value, boom, we're good to go. Okay? So very important to understand that it can't be 0. So selecting the right comparison is important. And let's do some examples to show that. But first, let's recall some infinite limits. If I ask you to find the limit as n approaches infinity of this, remember, it's all about the fastest growing term in the numerator and the denominator. This is the n cubed. It grows faster than the 2n. I don't care about it. 3n cubed will grow faster than the 50. We can rewrite this as the limit as n approaches infinity of n cubed over 3n cubed. This can simplify to be 1/3. Okay, so we're good with limits like that. We will see limits like that for the remaining series. Okay, so we have this series. It's n over 3n squared plus 20n. Does it converge or diverge? I don't know. But let's use the limit comparison to figure it out. Here's the key. We need to think about the limits as n approaches infinity of a sub n. What would it simplify to? If I looked at this guy, I would think, okay, well, it's n over 3n squared plus 20n. I wouldn't care about the 20n, right? It's going slower than the n squared. This simplifies to be 1 over 3n. This should be my guide for what series I should use to compare this to and to set up my quotient to find a value. Okay? Since I see 1 over n, I'm going to use 1 over n, which I know is the harmonic series and diverges, for the comparison. Okay? So watch what we'll do. We'll say this is A sub n, this is B sub n. Let's go ahead and divide the two. So n over 3n squared plus 20n divided by 1 over n. Okay, now what ends up happening and what you will do in the future is kind of skip this first step as writing it as a quotient and just immediately multiply by the reciprocal. Now what happens here is you're able to multiply those n's together, and we get n squared over 3n squared plus 20n. Okay, I will attempt to find this limit as n approaches infinity. If it equals a value, since this diverges, this is going to diverge. Okay, well, I know the 20n will go away. I have n squared over 3n squared. This will equal 1/3. This is that L that I'm looking for. It is finite. It is positive. Since it's finite and positive, and since 1 over n diverges, we will say this diverges by the limit comparison test. Let's look at the next one, root n over n squared plus 1. Now, what do I think about? I think about, okay, if I looked at this limit as n approaches infinity, I wouldn't care about the 1. I would just care about the n squared and the root n. Now, this is n to the 1/2, and this is n squared. This becomes n to the 3/2. Okay? This is going to be what I'm going to use for my comparison. Now, 1 over n to the 3/2, I know, converges. Why does it converge? Well, it's a p series, and this p is greater than 1. So I will go ahead, and you can immediately do this. Divide it by 1 over n to the 3/2, which is the same as multiplying by the reciprocal. I'll take the limit as n approaches infinity of root n over n squared plus 1 times n to the 3/2 over 1. This is dividing, okay? And then I will multiply the n's together. 3/2 plus 1/2 will get n squared over n squared plus 1. Now I look at this limit as n approaches infinity. The 1 won't matter. This just equals 1. This is perfect. This is finite. This is positive. So since this converges, this converges. Remember, they will both either converge or they both will diverge. Let's look at the next one, 4 over 3 to the n plus n. So I think about it, and I immediately go to that gets crossed off, and I have 4 over 3 to the n that I want to compare to. Well, I'm going to use 1 over 3 to the n, or 1/3 to the n, which I know converges. It is a geometric series with the r less than 1. Now let's see, I'd have 4 over 3 to the n plus n divided by 1 over 3 to the n, so that's times 3 to the n over 1. Now, let's just kind of do the limits as n approaches infinity. I'd end up with 4 times 3 to the n over 3 to the n plus n. This n won't matter. These would end up canceling, just giving us 4.
Premise interruption. Students, if you are not under the direct supervision of a teacher, coach, or sponsor, you need to exit the building at this time. Students, if you are not under the direct supervision of a teacher, coach, or sponsor, you'll need to exit the building. Administrators, if you'll do a hall sweep, I appreciate it. Thank you.
Okay, so this ends up being equal to 4. This is finite. This is positive. Since 1/3 to the n converges, this will converge. Okay, let's do another one like this. N over n squared plus 2 squared. I know if I do the limit out, it would be n over n to the 4th plus some other stuff, which will be smaller powers. this kind of simplifies to 1 over n cubed. I will use this simplified 1 over n cubed as my comparison. I know this converges. It's a p-series with the number greater than 1. So I look at the limits as n approaches infinity of n over n squared plus 2 squared times n cubed over 1. I am dividing, but we end up being multiplied. This gives us n to the 4th over n to the 4th plus some stuff. This cancels. The limit is equal to 1. So since this converges, I know this converges. Okay, this one we would use 3/4 to the n as our comparison. We would find that this also converges, because this is a geometric series and it converges. Finally, if we have something 1 over n to the 3p minus 1, if that converges, what can p be? Well, we know that 3p minus 1 has to be greater than 1. So we solve that, and we get p has to be bigger than 2/3. Okay? So limit comparison, very, very helpful. Direct comparison will definitely be helpful, but it's tougher to use. It will be used perfectly in certain situations. Then we have a p-series. If p is greater than 1, we know we're going to converge. And we have our integral test to also tell if we are converging or diverging. That's it. Thank you.